Hello, so today's lecture is on free vibration of a single degree of freedom system. Okay, so this is a single degree of freedom system without a damper. So that's why we call it undamped free vibration. Okay, it's free means there is no input to the system and there is no damper. That's why we call undamped. So this is what we call undamped free vibration single degree of freedom system. So let us take a look at the learning objectives here. Basically, we want to determine the equation of motion of a single degree of freedom system, of this undamped single degree of freedom system, natural frequency of it, okay, and how do you actually solve the equation of motion and understand the relationship between various solutions. As an introduction, of course, in any vibration analysis procedure, you need to generally have the mathematical model, derive the governing equations, find the solutions, and interpret what is the result. So basically, what's the relationship between the response. So a free vibration is produced and maintained by forces such as elastic and gravitational forces. So these forces depend only on the position and motion of the body. So when forces that oppose the restoring force, okay, for example, friction and resistance, are negligible, then we can call it as undamped. An undamped free vibration will repeat itself indefinitely. So in real systems, the frequency and the period of vibration obtained for a freely vibrating system are very close to the values obtained for a system that has a small value of damping. Okay, so that is how we actually assume it's an undamped. So let us take a look at if you have a block of M sliding frictionless on a horizontal surface, and vibration is induced by displacing the block at its distance, then releasing it with an initial velocity of x0, which is also equals to v0. So if you actually remember, maybe we can actually derive this equation of motion. So let's say I have this single degree of freedom system as shown in the notes here. How do you actually derive your equation of motion? So the first step is you have the assumed direction. You have to assume the direction. In this case, I've already drawn the assumed direction, which is going down. And then after that, you draw on the spring. So you don't draw the forces. You draw the forces on the spring, and then only you draw the action-reaction forces on the mass. So these are the basic how you can draw the free body diagram. After that, you write your equation of motion. Okay, so this part is basically your free body diagram. So how do you draw your free body diagram? Okay, following the steps, you have the assumed direction. So x is going down, that means you have to draw on the spring. So what happens to the spring? The spring has to go down, same direction as the assumed direction. So this is K. After that, the third step, so this is the second step. The third step is you draw action-reaction forces on the mass. So your force on the mass goes up. Okay, this is number 3. And then you have to write your equation of motion. How do you actually write your equation of motion? Is you write summation of forces equals to mx double dot. Okay, or in that case, your mx double dot is always positive. Okay, then your direction of forces going up is opposite, because going down going down is positive, so goes up is negative. So you have the force comes from the spring, which is actually the force is kx. So you have negative kx. Okay, there is no external forces, so you do not need to write any external forces. There is only one force. So when you actually write your equation of motion, you're focusing only on the mass, okay, to get your equation of motion. So if you rearrange that, you only have mx double dot plus kx equals to 0, because there's only one force there, which is kx. All right, easy peasy. So these are the steps on how you actually write your equation of motion with the steps on the free body diagram. So let us take a look at the notes here. All right, so that is how you derive this equation. So you should be able to follow the steps, and later on when you have more complicated system, so hopefully you can derive the equation of motion. So let us take a look at the general solutions for the previous equation based on this. So xt equals to a sine omega n t plus phi. So we have defined this in a previous lecture. And if you actually look at this, you can actually derive from the assumed solution xt, you can derive your velocity and your acceleration. And what you need to do, you substitute, okay, with this assumed solution, you substitute your x double dot into this formula, okay, as also your x into this formula. So you will get this expression. So you can take note here, because it is equals to 0, you can eventually have, you can see here, you have a common term of a sine omega n t plus phi. You can actually cancel it out, and you will end up with omega n is equals to, omega n squared is equals to k over m. Okay, maybe I can show you this one. So you bring, when you factor it out, you can bring both of these terms to the other side of the equation. So you get 0 divided by a sine omega n t plus phi. So you will actually cancel it out. So what you have left is just your negative omega, negative m omega square. You bring ka to the k to the other side, you get negative k, or you would have omega square is equals to k over m. So that is what you have in this equation. All right, so after that, this is what we defined just now. After we've got the equation of motion, what we want to get or calculate or characterize is basically this, what we call system's natural frequency. This omega n is what we call the system's natural frequency. So there are ways of finding the constants a and phi if you actually have initial values of at t equals 0. If you have the values of x naught and v naught, you can actually substitute into the equations to get those values. If you do that, there is a relationship between this a with the initial values that you can calculate, and it is given by these two equations. Okay, you don't have to memorize this in your list of equations. We normally give it to you. So this is the full solution. We can actually, if you remember, we already substitute your a and your phi into this full equation in terms of initial values. All right. So from those initial values, you can get the full expressions or the solution for your equation of motion. And these values has meanings to it. If you actually look at this figure, this is very important. Sometimes we give you a problem where you have to define what is your x naught, by just giving the graph like this. So if you actually look at the graph, you can get the initial value of your x naught, Okay, and you can also get the slope of V naught here, okay, or your initial velocity. So the slope is initial velocity, the height is your x naught, and then you can also get information from the graph. You can also get in terms of period, okay, and you can get maximum velocity here, okay, in terms of the slope. The amplitude, you can get it from the graph. Oh yeah, and also phi over omega n. If you look at this figure here, you can get this phi over omega n values. Okay. Then we take a look at the relationship as well. Since the solution repeats whenever the argument increases by an angle of 2 pi, there is a relationship of period of oscillation tau n is equals to 2 pi over omega n. And also the natural frequency of the oscillation in terms of hertz can be written as Fn equals to omega n over 2 pi. You can also express your full equations in terms of omega n, where if you remember your equation just now, the original equation of motion can also be written in terms of omega, yeah. Oops. Trying to write. If you remember the equation of motion, you have mx double dot plus kx equals to 0. So if you actually divide the whole thing with your m, so you have m divided by m plus km, x equals to 0. So you can actually see that this km is actually omega n square. Okay, x double dot plus omega n square x. So that is how you get this expression. So basically by dividing all through with your m. So this actually characterize the simple harmonic motion, okay, given by this relationship. So if you have a complicated system, you model it as a single degree of freedom system, you get the expressions, and whatever coefficients that you get, and you put it in this form, so you can actually predict its natural frequency. That's the idea of deriving it in that form. Okay, let me just skip this alternative solutions. Maybe you can read that part on your own. Okay, because we don't use that much. Okay, you also need to take note, this is a very important sections where you have you should realize that in my derivations of equation of motion just now, we do not include any mg term. So this is the explanation where you do not need to include your mg term in all your equations throughout this course, except for certain cases. Okay, I will let you know as we go along, but most of the time we are actually assuming that the displacement that we take is your x, okay, is actually defined at after what we call the static equilibrium position. So that is why mg is not considered, or you do not have to write the mg term. So this is the explanation where when you have a mass, first of all, it's under unstretched position, and this mass is, when you actually put it at the end of a spring, like as shown here, you're gonna have from the unstretched position, it will go down due to gravity, isn't it? So this is what we call this small delta, and this point here is what we call the static equilibrium position. So all our x is actually measured, okay, all our x throughout these courses is actually measured from this static equilibrium position. That means it's already beyond the mg effect. Okay, so the effect of mg is here. So that's why we can see the relationship between K delta is equals to mg. Okay, so mg is already taken care of, then only you measure your x. So that's why in all our equations, you may be either the mass is in this position or the mass is in this direction. Okay, both equation of motion should be the same. Okay, there is no effect of gravity, because in both cases we are measuring it from the static equilibrium position. So if you want to derive, let's say we are using this relationship, you can actually derive as mx double dot equals to, so this one you include the effect of the mg. So you can see that K delta is actually equals to omega. So this term actually will cancel out. Okay, omega w, sorry, it's not omega, it's w minus K delta. So you left out with just kx. So that's why you end up with the same equation. All right. So, and we have I've derived this equation previously, and you should be able to write your natural frequency from these expressions. And this is the relationship of how you would write it in terms of tau n and fn. All right, maybe it's good that now we take a look at one of the example where you have this heavy ring of mass moment of inertia of 1 kilogram meter square is attached at the end of 2-layer hollow shaft of length 2m. So this is the overview of the system. So we may want to write down what are the given parameters. So it says here mass moment of inertia. Okay, so take note that this system is a rotational system. So they also give you the shear modulus. So we know that mass moment of inertia is like your mass, but its rotational system is actually your G naught. Yeah, so 1 kilogram meter square, and at the end of the 2-layer shaft, so the length of the shaft is 2 meter, and they give you in terms of shear modulus of steel. So there are two G, shear modulus of the steel is G, so 80 GPa, and also you have brass of 40 GPa. And what you want to find is basically, here natural time period and torsional vibration. So what you want to find, so you can see this is the figure, and what you want to find is basically your tau n, natural time period, and your torsional vibration, and your omega n basically. Okay, your omega n and the tau n. So let us take a look. If you have this kind of problem, you want to find the natural frequency. So before you do that, you have two materials here, brass and steel. So you need to calculate the torsional stiffness for each of these. So this is actually combining the previous knowledge of whether this the stiffness is parallel or series basically. Yeah, because these two are torsional, so you can actually look at it as parallel. Okay, if you want, if I can draw it as such, it's actually kind of like parallel, because this thing is a rotational system, isn't it? So you have this brass and steel here, so you can see it kind of like the stiffness is actually in parallel. So if it's parallel, then you will need to get the summation of the K torsional for each of those brass and steel. So that's why you're using this equation. You get for the steel, you get the stiffness for the steel and for the brass. And you can add them up to get the equivalent stiffness. How do you actually get this equation is from the textbook. You can look for any standard tables on torsional stiffness for a hollow shaft. You can find this equation. Okay, and we gave to you as well all the parameters of the inner and outer diameter. So you can calculate the equivalent stiffness. From the equivalent stiffness, if you remember, we do have equations omega n equals to square root of k over m. But in this case, because this is a torsional system, so make sure you take note that for torsional system, it is actually using K torsional, in this case the equivalent stiffness, divided by J, okay, instead of M. So make sure you are aware that when you go from linear system, normally in the list of equations, we give everything in terms of linear system. But if it's torsion, you need to be able to convert from K become K torsional, M becomes J. So we can calculate the omega n of torsional natural frequency of the shaft, and then after that tau n is just 2 pi over omega n. So you can get the torsional natural time period of this system. Alright, so that's all for this lecture. Thank you very much.